Welcome to today's deep dive. We are really excited to have you joining us for this one.
Yeah, thanks for tuning in. I'm definitely ready to get into the weeds on this topic.
Awesome. So I want you to imagine a massive, 500-gallon gearbox in a steel foundry.
Oh, yeah. A real beast of a machine.
Exactly. It's encased in this thick iron, just roaring with power, practically vibrating the concrete floor beneath it.
You'd think it was indestructible.
Right. It looks completely impervious to the world around it. But that multi-million-dollar machine has this microscopic, almost biological vulnerability. It has to breathe.
It's a great way to put it.
Yeah, so today we are looking at a technical specification sheet for a very specific, highly engineered piece of hardware, the DES-CASE VentGuard Series breathers.
And it's a fascinating piece of tech.
It really is. Okay, let's unpack this, because for anyone managing heavy infrastructure, or frankly, anyone just fascinated by the hidden mechanics of the built world, this spec sheet tells a wild story.
It absolutely does.
It shows how preventing catastrophic industrial failure doesn't come down to, thicker steel armor. It comes down to tiny, passive, brilliant engineering choices that regulate how a machine interacts with the air around it.
Yeah, and the premise that a machine actually breathes usually catches people off guard.
I mean, I was surprised by it.
Right, because we look at pulp and paper mills or forestry equipment, food and beverage plants, and we just see closed-loop systems.
Just a bunch of sealed metal tanks and heavy hoses.
Exactly. The assumption is that the hydraulic fluid, or the gear oil inside, is entirely walled off from the ambient environment, like it's in a vault.
Which makes sense intuitively.
Sure, but in fluid dynamics, a completely sealed tank is basically a bomb waiting to happen, or a vacuum waiting to implode. The system absolutely must exchange air with the outside world.
Okay, I want to challenge that slightly, though, because if I have a hydraulic press, the fluid is just moving from the reservoir into a cylinder and then back again.
Right.
It's all contained within the machine itself. So why does external air need to enter that loop at all?
That's a great question. It really comes down to volume displacement.
Volume displacement, okay.
Yeah, let's look at that hydraulic cylinder extending to lift a heavy load. It requires a massive volume of fluid to be rapidly pumped out of the main reservoir to fill that extending cylinder.
Oh, I see.
As that fluid leaves the tank, it creates a physical void. And, nature abhors a vacuum.
It has to fill the space.
Exactly. To prevent the tank from buckling inward, ambient air from the factory floor must rush in to fill that empty physical space.
It makes perfect sense.
And then, a few seconds later, when the cylinder retracts, all that fluid rushes back into the reservoir. It reclaims its space, and the air that just entered is violently pushed back out through the exhaust port.
So the machine is basically functioning like an iron lung.
That is a perfect analogy.
Yeah.
Every mechanical action forces an inhalation and an exhalation. But what if the machine is off?
Because the spec sheet specifically targets intermittent operations, right? Like machines that run in bursts and then sit idle. If the fluid isn't moving, the machine isn't breathing, so the threat just goes away.
That is a very common misconception, actually.
Yeah.
And it's exactly why intermittent operations are so dangerous for fluid health.
Really? Why?
Even when a machine is completely powered down, it experiences something called thermal breathing.
Thermal breathing? I'm assuming that relates to the ambient temperature of the factory.
It does. Let's say that steel foundry heats up by 30 or 40 degrees during a daytime shift.
It gets pretty hot in there.
Right.
Ugh.
The air trapped inside the headspace of the idle machine's reservoir expands as it gets hot. The machine essentially exhales.
Just from the heat expanding the gas.
Exactly. Then the night shift rolls in, the factory cools down, and that internal pocket of air contracts. This creates a slight vacuum inside the tank, and the machine slowly inhales the cooler and often much more humid night air.
Oh, wow. That makes the ambient environment the primary threat.
100%.
If this machine is sitting in a humid, dusty paper mill or like a forestry site surrounded by dirt, every single thermal inhalation is dragging water vapor and abrasive dirt directly into the reservoir.
And historically, equipment just had an open tube or a basic dust cap to allow this airflow.
That's crazy. That means a machine sitting idle for a week is just passively pulling in moisture every single night.
Which brings us directly to the core technology of the VentGuard series we're looking at today. The defining feature that separates this from a standard open breather is the integrated check valve system.
This is the 0.1 sci thing, right?
Yes. These units completely isolate the internal reservoir from the external environment. They are not open pipes at all.
Right.
They only open to allow air in or out when the pressure differential, which is the difference between the inside of the tank and the outside atmosphere, reaches exactly 0.1 psi.
Which the specs say is about 0.007 bar.
Correct.
Wait, I'm stuck on the 0.1 psi threshold because that is an incredibly tiny amount of pressure.
It is very slight.
If it is that sensitive, how does the valve not just flap open every time a heavy forklift drives by and shakes the floor?
That's the brilliance of the engineering. It's a purely mechanical calibration using spring tension and specialized elastomer umbrella valves.
Elastomer umbrella valves, that sounds highly specialized.
It is. The valve relies on a highly specific delta P, or change in pressure. The physical spring holding the seal shut is engineered to resist ambient vibrations and those baseline atmospheric shifts.
Okay, so a forklift won't trigger it.
Right. It requires a sustained directional pressure difference of 0.1 psi to physically overcome the spring tension and deflect the elastomer seal.
I get it.
Until the internal tank pressure drops exactly 0.1 psi below the outside air, the valve remains perfectly seated. It's a closed loop. No morning dew, no airborne dust from a passing truck can get in.
So it's essentially functioning like a scuba diver's regulator.
Yes, exactly.
Because a scuba regulator doesn't just free flow air into your mouth, it's a gatekeeper. It holds back the pressure of the tank until you create a slight vacuum by inhaling.
That's a really good way to visualize it for the listener.
The VentGuard just holds its breath until the very last millisecond the machine actually needs to equalize its internal pressure.
That analogy translates perfectly to pneumatics. The machine demands air, the valve cracks open, and the pressure equalizes. But here is the kicker.
Yeah.
When that valve does open, the incoming air doesn't just get a free pass. Before it ever reaches the reservoir, it hits a highly advanced filter.
Okay, let's look at the filter. The spec sheet notes a 3-micron absolute filter efficiency using polyurethane and polyester media.
Yes, 3 microns absolute.
When we talk about industrial filtration, 3 microns sounds small, but I think we need some real-world context for you listening. Because if we are prepping for an engineering meeting, we can't just say, it's smaller than a human hair.
No, you need the operational context.
Right. We need to know why 3 microns matters for a gear pump.
We can map that directly to the mechanical tolerances inside heavy machinery. A standard high-pressure hydraulic pump might have dynamic operating clearances, which are the microscopic gaps between the moving metal parts of roughly 5 to 10 microns.
5 to 10 microns. Okay, so if a 15-micron piece of silica dirt gets sucked through an open breather and enters that fluid...
It acts like a microscopic metal shredding wedge.
Oh, man.
The particle is physically larger than the gap between the gears. So as the gears turn, they literally crush that dirt particle into the metal surfaces.
That sounds expensive.
It gouges the steel, which creates more metal shadings, which then create more gouges. It is a cascading catastrophic failure.
Which totally explains the absolute rating on the spec sheet. It's not catching most 3-micron particles. It is rated to stop virtually all of them.
Exactly.
A 3-micron absolute filter guarantees that nothing large enough to bridge a 5-micron mechanical clearance will ever enter the system.
And this highlights why these specific breathers are so critical for those low to medium flow intermittent applications we discussed earlier.
Because they sit idle so much.
Right. In a continuous flow system where air is rushing in and out nonstop 24/7, the check valves would just be held open perpetually.
They'd never close.
Yeah. But for a pump that fires up in bursts, or a gearbox subjected to massive thermal shifts day and night, sealing the system with a 0.1 psi check valve when it's idle is basically the difference between your hydraulic fluid lasting 5 years versus 5 months.
That is a massive return on investment.
Absolutely.
Well, if this check valve and 3-micron filter combination is so protective, let's talk about scale.
Let's do it.
Looking at the lineup in the source material, there are 5 specific product codes. They are divided into 2 categories based on size. You've got the miniature models, the DCVG-BB, and the DCVG-1, which use a 3/8-inch multi-fit thread.
Right, the smaller ones.
And then you step up to the standard models, the DCVG-2, DCVG-3, and the mighty DCVG-4. Those utilize a larger 1-inch multi-fit male thread.
And I just have to say, the inclusion of multi-fit threads is a brilliant nod to global industrial maintenance.
How so?
They are engineered to mate with various plumbing standards around the world. NPT, BSPT, BSPP.
Ah, so you don't need a million adapters.
Exactly. A maintenance manager in a plant in Stuttgart and one in Chicago can likely thread the exact same VentGuard model onto decades-old legacy machines without having to source highly specific proprietary adapters.
That makes procurement a lot easier, but here's where it gets really interesting to me. I'm looking at the sizing recommendations.
Okay.
The miniature DCVG-BB is rated for a 2-gallon hydraulic reservoir, but the massive DCVG-4 standard model is rated for a 500-gallon gearbox.
That's a huge range.
It is. If I'm a plant manager and my primary goal is absolute bulletproof protection for a 50-gallon tank, why wouldn't I just buy the giant DCVG-4 and slap it on everything?
It seems logical, right?
Right. Isn't a larger filter area and more desiccant always superior?
Yeah.
Why even manufacture the miniatures?
What's fascinating here is that in fluid dynamics, over-engineering the hardware without respecting the airflow metrics can actually destroy your equipment faster.
Wait, really? It can destroy it?
Yes. Sizing is a delicate, highly calculated balance. If we look at the engineering notes and the flow rate charts provided in the specs, there is a precise, immutable relationship mapped out between flow rate measured in SCFM, standard cubic feet per minute, and the pressure drop, or delta P.
Because pushing air through a 3-micron filter media and forcing open a spring-loaded check valve inherently creates physical resistance.
Precisely. It is the exact opposite of a free-flowing open pipe. That resistance causes a pressure drop. The charts show the maximum airflow at a delta P of 1 CS.
Okay, I see that.
For the miniature units, that maximum safe airflow is 1 cubic foot per minute. For the standard units, it jumps to 11 or 12 CFM.
Oh, that's a big difference.
Huge. If you mount a Massey standard breather designed to breathe 12 CFM on a tiny 2-gallon system, the physical footprint alone is absurd. You are trying to step down a 1-inch thread to a 3/8-inch port.
You'd have this giant tower of brass fittings.
Exactly, creating a vulnerable tower of fittings that could easily snap off if bumped by a worker.
But the reverse scenario seems much more dangerous to me.
It is.
If I'm a purchasing manager trying to cut costs, and I order a pallet of the miniature breathers to install on a massive centralized lube system, displacing 90 gallons of fluid a minute.
You're basically choking the machine to death.
A severe pneumatic bottleneck.
Yeah. The massive hydraulic cylinders retract, and the reservoir demands 10 cubic feet of air instantly to fill the void. But the miniature breather can only physically permit 1 cubic foot of air through its tiny check valves and restricted filter area.
So the fluid is leaving the tank faster than the air can replace it.
Yes. The tank pressure drops violently. You create a severe vacuum inside the reservoir.
And vacuums are bad news.
Terrible news. When a powerful hydraulic pump tries to pull viscous fluid from a reservoir that is under a vacuum, you trigger cavitation.
Cavitation, that's when the pressure drops so low that the fluid essentially boils at room temperature, right?
You nailed it. It forces dissolved air and vapor out of the hydraulic fluid, creating millions of microscopic bubbles.
And those bubbles travel into the pump.
Right into the high-pressure side of the pump, where they violently collapse. The physical shock waves of a collapsing cavitation bubble literally blows microscopic chunks of steel off the inside of the pump housing.
Oh, wow.
It sounds like marbles rattling around inside the machine. And it will destroy the equipment from the inside out in a matter of hours.
That is wild.
So sizing these breathers isn't just a casual recommendation. It is mission-critical fluid mechanics. You have to map the exact fluid displacement rate of your machine to the SCFM flowcharts in this spec sheet.
You're regulating the breath without choking the machine.
Perfectly said.
Knowing how precisely these need to be sized leads us to the ultimate question of physical endurance. What exactly is sitting inside these housings, doing all this complex filtration and moisture removal while surviving in these unforgiving environments?
The environmental operating specs are brutal, honestly.
I can imagine.
These units must maintain their structural integrity and chemical filtration properties from -20 degrees Fahrenheit all the way up to 200 degrees Fahrenheit.
Wow.
That is -29 to 93 Celsius.
I noticed the housing material isn't just standard injection molded plastic. The specs note the core structure utilizes polycarbonate, along with nylon 6/6 that is 30% glass filled.
Yeah, that glass-filled nylon is key.
Because that's what you find in heavy-duty power tool casings, right? Or automotive intake manifolds.
Exactly. The addition of glass fibers to the nylon matrix drastically increases the tensile strength and thermal stability.
Which is necessary when bolted to heavy machinery.
Think about it. A breather bolted to a high-speed gearbox is subjected to constant high-frequency harmonic vibration. Standard plastic would fatigue, become brittle and crack.
Which would completely compromise the zero point 0.1 sisi seal.
The glass-filled nylon ensures the housing can take physical abuse and constant thermal cycling without warping.
So the rugged housing protects the valves. But the active ingredient doing the heavy lifting against the invisible threat of moisture is the hydrophilic media inside that polycarbonate cylinder, silica gel.
We all know silica gel from the little paper packets in a new pair of shoes.
Right. Do not eat.
Exactly. But deploying it on an industrial scale relies on aggressive adsorption chemistry. While the polyurethane filters are physically blocking the solid dirt particles, the silica gel is acting as a chemical trap.
How does it actually trap it, though?
The surface area of silica gel is immense. It's millions of microscopic pores. As the humid incoming air passes through the bed of desiccant, water vapor molecules are physically drawn into these pores and trapped, stripping the air of moisture before it ever reaches the oil.
And the spec sheet mentions this really cool visual color indication. It shifts from blue to pink.
Yeah, it's very clever.
I like to call it an industrial mood ring. But how does that actually work mechanically? I mean, it's not an electronic sensor.
No electronics at all. It relies on a chemical indicator impregnated into the silica gel itself.
Oh, okay.
Traditionally, this was something like cobalt chloride, though modern iterations often use safer, REACH-compliant equivalents. When the silica gel is dry, the electron configuration of the indicator chemical absorbs certain wavelengths of light, reflecting back a deep blue color.
So blue is good.
Blue is very good. But as water molecules bind to the chemical matrix, the physical structure of the compound changes. This hydration alters how it interacts with light, causing it to reflect pink wavelengths instead.
If we look at this from the perspective of factory maintenance, that visual shift is brilliant.
It's a game changer.
Because if you have a technician walking a floor with 200 gearboxes, they don't have time to unthread every single breather, take an oil sample, or wire up digital moisture sensors to every machine.
Nobody has time for that.
They just walk the aisle. Blue means the chemical trap is active and protecting the machine. Pink means the silica gel is saturated. It has trapped all the water molecules it can hold, and ambient moisture is now bypassing the filter.
It takes a microscopic chemical reaction and turns it into a massive, undeniable binary signal.
It's just so simple and effective.
It entirely removes the guesswork from preventative maintenance, and the sheer volume of water these units pull out of the air is staggering when you look at the raw capacity numbers.
Okay, let's run those numbers because the capacity breakdown is pretty wild.
So on the absolute smallest end, the miniature DCVGBB breather contains just 0.1 pounds of desiccant.
That's about 59 grams, not a lot.
Right. Yet that tiny volume of silica can chemically trap 0.8 fluid ounces or 23 milliliters of water.
That is almost a full shot glass of pure water.
It doesn't sound like much until it's in your oil.
A shot glass of water mixed into a sensitive 2-gallon hydraulic lube might not sound like a lot, but it will absolutely wreck the fluid's lubricity and initiate rust on the internal valves.
Now scale that up to the Titan of the series, the DCVG4 standard breather. That unit holds 2.0 pounds of desiccant, roughly a full kilogram.
Okay, a huge jump.
Its maximum water retention is an incredible 12 fluid ounces. That is 356 milliliters.
Wait, that is an entire standard soda can's worth of water.
Yes. Imagine taking a sealed can of water, walking up to a multi-million-dollar steel rolling machine, popping the tab, and pouring it directly into the main gear oil reservoir.
That would be a fireable offense.
Immediately. But that is exactly what the ambient factory air is trying to do over the course of a few months through thermal breathing.
It's just sneaking it in.
The VentGuard forces the air through the check valve and then forcefully captures that entire soda can of moisture, lacking it chemically inside the pink silica gel.
That really puts it in perspective. And the spec sheet explicitly states these units are REACH compliant, adhering to stringent European chemical safety standards.
Which is crucial for global operations.
Absolutely. They are fully compatible with mineral oils, most synthetic oils, and diesel fuels. The internal seals utilize Buna-N, EPDM, and silicone.
Ensuring that the caustic fumes evaporating off the factory's oil don't just eat the breather from the inside out.
So, what does this all mean? We started this deep dive by looking at iron beasts. We see a 500-gallon gearbox, and just assume its reliability comes from thicker steel walls and massive gears.
But it's not the steel that saves it.
Right. What the source material reveals is that protecting heavy industry actually requires controlling the microscopic, invisible variables. It requires a highly calibrated elastomer check valve that cracks open at exactly zero point 0.1 psi to let a machine take a filtered breath.
It requires glass-filled nylon housings to survive vibration.
And silica gel that chemically alters its light absorption from blue to pink, just to trap a soda can's worth of water before it triggers catastrophic cavitation or rust.
It entirely reframes the concept of a sealed system. These massive machines are highly dynamic, constantly interacting with and defending against the very air in the room.
If you're an engineer designing a pneumatic system or a plant manager trying to extend the life of your legacy equipment, you have to account for thermal breathing and fluid displacement. You just have to respect the delta P flowcharts.
You really do.
Yeah.
And, this raises an important question, and it's a concept I want you, the listener, to mull over long after we wrap up today.
Lay it on us.
This deep dive proves that large industrial machines, in a very literal mechanical sense, inhale and exhale the environment around them to balance their internal pressures.
Yeah, the iron lung.
Right. It makes you wonder, what other supposedly closed systems in your everyday life are doing exactly the same thing?
Oh, that's interesting.
Think about the transmission casing in your car, the sealed compressor in your home refrigerator, or even the weather-sealed electronics sitting on your desk. They are all subjected to daily temperature shifts and the resulting thermal expansion.
Are they secretly breathing the ambient room air right now?
Exactly. And if they don't have a 3-micron absolute filter and a desiccant trap, what microscopic assassins are they pulling in with every single breath?
That is a slightly terrifying but awesome thought. Next time you look at a heavy machine, or even just your own car parked in the driveway, remember as the sun goes down and the metal cools, it is breathing.
Something to think about.
Definitely. Thanks for joining us on this deep dive. We will see you next time.